Okay, we're now going to look at nuclear energy, and the first type we want to look at is nuclear fission. So there's two types of fission there. Now fission means the splitting of the nucleus there. So when you're focusing on this, imagine a nucleus inside an atom like a uranium nucleus with 92 protons and a total of 238 or 235 nucleons. Now it's the 235 one that actually is the easy one to split if there's a slow moving neutron. So the neutron comes through here to actually strike into a uranium-235 nucleus. That will induce a fission because this will actually start to wobble and elongate a bit like this. And the total electrostatic repulsion between the protons will force this to split into two halves, roughly in half. Now, typical sort of size will be 56 and 36 in terms of the number of protons. So you've got barium and krypton, okay? So there's a range of different daughter nuclei that can be produced in this splitting process. And in each case, the mass afterwards is slightly less than the mass beforehand. So there's a mass defect there. And that mass drop again will convert into energy in the form of E equals mc squared. So you're going to release energy by that one fission, that one split of a nucleus. Now that's induced fission. Okay? This neutron has actually struck here, caused us to change to U-236, slightly wobble that, and the overall electrostatic repulsion now actually pushes the nucleus apart into two halves. Now, they're not equal halves, by the way, and also releases neutrons here. This particular one, I think, releases 3 neutrons. But it typically releases 2 neutrons in this reaction, and it can release up to 12 neutrons, depending on the daughter nuclei produced. Spontaneous fission happens naturally where a nucleus on its own suddenly splits into two halves. So this occurs for large nuclei that are unstable. Well, we're focusing here on trying to induce fission here. So there's an example of one there. It doesn't show the unstable wobbling before that splits. It's also sort of referred to as a liquid drop model where it becomes unstable and just sort of splits apart, okay? Now that particular animation came from chemistry.com, all right? You can also draw it like this here. This is the one off the smartboard, a neutron colliding with a U-235, typically releasing 2 smaller nuclei, the daughter nuclei, and some neutrons and some energy because of the mass loss. Right? So that's the process of fission there. Spontaneous, naturally occurring, induced by a neutron striking it. So let's look at the fuel you need to use in your nuclear reactor. So we've got to use very large elements there, so they've got large nuclei that are easier to split. So uranium-235 is that fissionable fuel that we want to use. So our problem here is that most of the actual stuff you mine is 238. All right? Less than 1% would be this 235 in this natural uranium that you actually mine. So you need to go through an enrichment process to actually increase the proportion of this fissionable U-235 in your fuel. So from memory there, it takes a couple of years to actually go through this chemical process. I think it involves a centrifuge as well, where you're going to take your mined uranium-238, which is mostly this, and improve that percentage there of less than 1% 235 to around about 3% 235. So it takes a long time to do that. You want to increase that proportion of U-235 that's actually in your fuel there. Now once you've done that, you put that into uranium pellets then. You've got pellets of uranium which have got a greater percentage of 235 than normal then, and that goes into a fuel rod. I think it's a steel contained rod there, about 6 feet long, and that's going to be your fuel rod going into a reactor core. Now there's a second issue here in our design. We need to think about slowing the neutrons down. Now if you can get those neutrons that are released in that first fission to go and actually induce other fissions with other uranium nuclei, you can get what's called a chain reaction here. So what we're trying to do here is when this nucleus splits, this uranium, due to a neutron striking it, the extra neutrons that are produced in that reaction, if they can go and strike other uranium nuclei and cause them to split, and release energy again and release even more neutrons, which go on to reduce further fissions, then we're going to get a chain reaction there. And this is what it looks like here. Neutrons are the green ones. You can see one neutron splits one here. That's going to split more and so on. It's going to spread through that very quickly there, releasing lots of energy for each fission. And we're talking mega electron volts for just the one fission there, so it's a lot of energy. In the notes here, we've got spontaneous fission there. Spontaneous when a large nucleus splits of its own accord there. And it goes into 2 smaller nuclei, and releases some extra neutrons, but it's converted into energy, the missing mass that's lost, okay? And that's by E equals mc squared, okay? So that's a spontaneous one. Now in the induced one, a neutron is actually becoming absorbed by the uranium nucleus, becoming unstable as a moving or wobbling 236 unit nucleus, and then splitting into daughter nuclei with extra neutrons and the missing mass the mass defect, is converted into energy. We've got about 1 million times the amount of energy there being released compared to a chemical reaction in coal. So a very small amount of this, say 1 gram of this uranium fuel, will be the equivalent of 1 tonne of coal. Now this fission occurs because very large nuclei have got a total repulsive force that's going to challenge the nuclear force. And if that wobbles at any degree and becomes a total force in one direction or one dimension, if you like, it causes the electrostatic force to overcome the nuclear force holding it together, and you get this splitting effect there, okay? So you can sort of think of it as being like that diagram there. As I said, a chain reaction is possible. So what we're trying to maintain here is for every neutron that's captured, another one that's able to split is released, okay? And you're getting a chain reaction that's possible in that case. Something to bear in mind is that this actually works for slow-moving neutrons for the capture. So you really want slow-moving or thermal neutrons to be involved in this chain reaction here. So if you're trying to build a bomb, that's one thing, where you're going to have a huge explosion and a huge uncontrolled reaction there, or chain reaction. We want to control the chain reaction. So we want to first of all slow the neutrons down. So to do that, we need what's called a moderator. Something in this nuclear reactor we're designing to actually slow down the neutrons. So you can use heavy water for that. They also use graphite, which is carbon, to slow down the neutrons. Heavy water is very good, H2O, because if you think of it, normal water would have oxygen and 2 hydrogens. When a neutron collides with that, it's going to cause this to recoil, absorbing some of the kinetic energy and momentum, and this will go off slower as a reduced kinetic energy, which is what we want. We want this to be moving with less energy. So water is a similar size mass to the neutron. It's not too different. You look at a neutron that's got a mass of about 1 then. If you're looking at this, you've got oxygen is 16 there, and you've got 2 hydrogens, which are 1 and 1 in their mass. So it's about 18 to 1, so not too bad. It will actually recoil there. So you want something relatively small as a molecule here that's going to recoil, or in the case of carbon, an atom. Okay? So size is important. So this does actually absorb some of the kinetic energy. The reason they don't use normal water, because it's actually going to absorb some of those neutrons into the hydrogen. You'll find hydrogen becomes H2 if the neutron hits it. We do not want to absorb neutrons because we want to try and sustain the chain reaction. So rather than actually sort of use normal water, we use a form of heavy water where we're using H2 deuterium to start with. We're going to use 2 of those to oxygen to form this heavy water. So that's already got a neutron in there, so it's less likely to absorb the neutrons in that neutron flow in the core, so therefore it's going to sustain the reaction better, the chain reaction better. So let's look at a reactor now. We've talked about the idea of having the fuel rods going in, so it's about 3% of U-235, as opposed to a naturally occurring one that's less than 1%. We've got a moderator in here. This particular one is a graphite moderator, which is carbon, so you would actually drill holes in there and lower the fuel rods into that. But as I said, they normally use heavy water as well around the world, so there's a couple of types of moderators. And what we're going to do here is we're going to pump water around this to actually get heated up by the energy released in the reaction, as opposed to coal. So in this part of the process, it's going to be the same from here on. Coal heats water to steam. That actually goes through a pipe, turns a turbine generator, so you think of a fan blade. That turbine spins. On the axle attached to that, you've got wires that turn past magnets, and you generate electricity in the wires for power transmission. From here on, that's the same here. Instead of burning coal, we're going to use a nuclear reaction to heat the water to steam. And we actually have this in a pressurised vessel, so it goes well above 100 degrees and it doesn't boil. You take that to a heat exchanger, and here we're going to heat water into steam. So it's a separate unit, if you like, so the water doesn't get contaminated in this area here. It's only this water here is sort of contained within the vessel and goes past the core walls and may pick up contaminants. We're trying to keep that away from the outside environment here. So we've avoided actually absorbing the neutrons because we're using heavy water, so the H2 does not absorb the neutrons. You can also have a reflector blanket around here that actually reflects the neutrons back in to increase the chances of that chain reaction going on. We want to get the neutrons captured and increase the number of nuclei that are split. However, you can get too much of a good thing, and this could actually melt down by overheating and literally start to melt down through the floor because of being superheated. So we need to control the rate of this reaction so that it's actually not too hot when we don't need it to be too hot. So there's a thing called control rods here that go in between the fuel rods there, and you can push them in and you can pull them out to control the rate of the reaction. So what do you think they do? They're made of cadmium and also boron is another possibility, but they're really good at absorbing neutrons. They absorb neutrons. So obviously the further in they are, the more neutrons are going to absorb between the uranium rods there, and you're going to slow down that chain reaction. So neutrons would normally cross between the rods there, getting slowed down by the moderator, okay, due to collision, being slowed down where the hydrogen would recoil, the water would recoil. By putting the control rods in there, you can start to absorb some of those neutrons and control the rate of the reaction. So if it's 6 o'clock at night and everyone's just got home, they put the TV on and you've got the food going, you need to have these control rods further out because you need to generate more electricity, you need more heat, and that'll be used up here by the turbine and taken away as power. If it's the middle of the night though, we want to actually sort of slow that down because not many people are using electricity, so you push the control rods back in. Now this is actually monitored by, I think they monitor neutrons. People used to hand put these in and out, but I'm pretty sure it's controlled by a computer now, that sort of stuff, something for you to check out. Alright, so don't forget, for the chain reaction here we need to get those neutrons slowed down, so we need some sort of a moderator. And don't forget they're going to come with a very high speed because that energy there is going to go to kinetic energy of the products. So we must slow them down with a moderator, like that heavy water. There will be some gamma rays produced as well if the nucleus is in an excited state. So picture the chain reaction like that. Okay. The moderators, a good moderator needs to be slowing down the neutrons. Okay. So it needs to be a smaller molecule, if you like, or have a small mass to recoil, and it needs to not absorb neutrons too much. So they've got that in the notes. You need a low mass there so it recoils more easily and absorbs that energy, and it needs to not be a good absorber of neutrons. So this is a poor absorber of neutrons, so it's very good to use, and that's a typical example of the picture there. So something else to note is that many neutrons might be absorbed by the surrounding U-238 nuclei because they can turn to U-239. So you have got an issue of trying to maintain that chain reaction, and that's why it's important to have some sort of a core there with a reflector blanket that can actually reflect the neutrons back in through there so that we do get maximum use of the neutrons produced. And obviously we need to slow them down there. There is a thing called critical mass, by the way, that if you have too small an amount of that U-235, you won't actually get enough neutrons going on, enough chain reaction to maintain it. Okay, so we're trying to get that enrichment going on as well to 3% so that we are successful. We don't want to go too high with this, by the way, because you can get an uncontrolled chain reaction that's really very high and you could get a bomb out of that. So we don't want to have too pure a U-235 there. Now I've gone through the components of this. So we've talked about the fuel being U-235. Okay, we've got to do an enrichment process to get that pure enough or increase the proportion of that in the actual fuel. We talked about the moderator type there, okay, heavy water or carbon graphite, to slow the neutrons down to maintain the chain reaction. Okay. We talked about control rods being able to be put in there to absorb and control the rate of the reaction, slow down that reaction rate. Now, what we haven't talked about here is that about 1% of all neutrons are emitted from the daughter nuclei after a delay of more than 10 seconds. Now, that's really important because if it was instant, we wouldn't have time to actually control that rate of reaction and change the level of the control rods. We want to have time to actually have the control rods go in and slow down the rate of reaction, keeping it just above 1 to 1. Any rate increases are only about 1% per second, and that's got enough delay to actually control it. Outside that, we need to then shield the radiation from the rest of the people coming out there. So there is a radiation shield enough to actually absorb alpha particles, beta particles, and more importantly, gamma particles. So you've got a few feet of steel and concrete around that core as a radiation shield. There's a thermal one to reduce the damage to the core walls, and there's also a biological shield there to stop the gamma rays coming out there. So there's actually two shields.